So in the last lecture, we discussed about thermal expansion. And in thermal expansion, we discussed about linear expansion. The principle of linear expansion is that fractional change in length is equal to coefficient of linear expansion multiplied by change in temperature, or the length at a certain temperature T becomes length at a temperature T naught into 1 plus alpha into T minus T naught. Okay, then surface expansion, which happens according to the principle that the fractional change in surface area is coefficient of surface expansion into delta T. So the surface area at a certain temperature T is equal to original surface area into 1 plus beta into T minus T naught, where the coefficient of surface expansion is double of alpha. And finally, volume expansion. Where fractional change in volume is equal to gamma delta T, or the volume at some temperature T is the original volume at T naught into 1 plus gamma into T minus T naught. And gamma is equal to 3 times alpha. So let's start with a simple example today. So we have a solid metallic sphere of radius, some kind of value of radius is given to us. Say the radius is at a temperature of 5 degrees C. So if the coefficient of linear expansion of the metal is alpha equal to 8 into 10 raised power minus 6 per degree C, then find its radius at a temperature of 55 degrees C, percentage change in its radius, percentage change in its diameter, then percentage change in its surface area, and finally percentage change in its volume. Let's understand this question. So the formulae that you require for this are all above. So just try this question out quickly. We'll discuss. Yeah, so anybody worked out the answer, please let me know. So for the first one, you can just use the formula that radius at a new temperature T will be equal to the original radius into 1 plus alpha into temperature change, or the change in radius upon original radius will be alpha delta T, because radius is a length dimension. No? Okay. So you can calculate it this way also. You can see that so alpha is 8 into 10 raised power minus 6, and the temperature change is 50 Kelvin or 50 degrees C. So this is 4 into 10 raised power minus 4. Okay. So the change in radius is 4 into 10 raised power minus 4 times the original radius, which is 250 centimeters. So that's 10 raised power minus 1 centimeter, or 0.1 centimeter. So yes, your answer is correct. The new radius at this temperature of 55 degrees C will be the original radius at 5 degrees C into 1 plus alpha delta T. So this will come out to be 250.1 centimeters, because this was as much. So also from this we can see that the percentage change in radius, the second part, you can see. Oh, sorry, this is the first part. Okay, so the second part. So this is 0.04%. Yes, very good, Kunj. That's correct. Okay, now let's work out the other parts of the question. So we can understand that radius R and diameter, let's say D. So D is equal to twice of R. These are both linear dimensions. That is, dimension of radius is also length. Dimension of diameter is also length. Okay. So So therefore, this is also alpha delta T. This is also alpha delta T, which is 4 into 10 raised power minus 4. So therefore, delta R by R percentage change is equal to delta D by D percentage change is equal to 0.04% increase for a temperature change of plus 50 degrees C. There's a 0.04% increase in radius or in diameter or any linear dimension for that metal. Okay. Whereas when we talk about surface area, you can see that this will have this kind of percentage change. Okay. So surface area's percentage change will be twice of linear dimensions percentage change because beta is twice of alpha. And likewise, the volume percentage change you can see that the percentage change in volume is a 0.12% increase for delta T equal to plus 50 degrees. Okay, now let's understand another type of question. So metallic scale okay, I'll just take you back to this section so you can write this down. Okay. Okay, let's understand an application question now. So metallic scale is calibrated to measure length with 100% accuracy at a temperature of 20 degrees. So it is used to measure the length of a wooden plank at 20 degrees C and measures L equal to, let's say this one. Okay. Now the measurement is again repeated at a temperature of, just a minute, we'll make this 400 centimeters. So at a temperature of 80 degrees C. Okay. So given that alpha for the metal is suppose 9 into 10 raised power minus 6 per degree C, and alpha for wood is equal to 3 into 10 raised power minus 5 per degree C. So first thing, find the true length of the wooden plank at this temperature. Find the measurement made by the metal scale at T equal to 80 degrees C. Okay. So the hint to you is that this will be a false measurement. This will have error because the scale was calibrated at 20 degrees C and has expanded at 80 degrees C. So next we have to calculate the percentage error in the measurement. How much is the percentage error made in this measurement, which is done at 80 degrees C using the given scale? So just try out this question. Okay, so let's understand this question. So the first thing you have to pick up here is that with the temperature rising, the scale also expands as well as the actual wooden plank that expands. So as a result of that, the measurement made by the scale is not going to be accurate, and that's why we are talking about a percentage error in the end about it. So it's like, let's say this is our scale, which was calibrated at 25 or whatever 20 degrees C. So this is at 20 degrees C. The least count, that is the smallest division here, the least count of the scale, or one division of the least count, is actually equal to 1 millimeter or zero point 0.1 centimeters. But at a new temperature, which is in this case 80 degrees C, the scale expands. So the least count, or one division on the scale, that becomes 0.1 centimeters into 1 plus alpha of metal into delta T. Okay. Now the wooden plank that we are using to measure, that we are using the scale to measure the length of, that wooden plank has a length of 400 centimeters. That's the true length at 20 degrees. So the wooden plank also expands to a length, let's say L prime to delta. So that length will become 400 centimeters into 1 plus. Now let's pick up the values of alpha for the two of them and substitute here. Okay. Yeah, 9 into 10 raised power minus 6 for the metal, and 3 into 10 raised power minus 5 for this. Temperature change of 60. So this will be the true length. Okay. But then the least count of the scale, this has become the least count. So the measurement made by the scale is the true length divided by the least count. That is L prime divided by 1 division. So L prime is the original length into 1 plus alpha of wood into delta T. Whereas this is 1 millimeter into 1 plus alpha of metal into delta T. So this is the measured value. Let's say this is X. So you can see that this is going to be different from this. When we calculate this, okay. So bring this to the numerator by putting the power -1. And now to make the calculation easier, rather than substituting this, which is going to be difficult, just a second. Okay, so as you can see here, this calculation is going to be very lengthy. Okay, because we'll have to do something like this. So we are going to use an approximation method instead of substituting this over here. We are going to use an approximation method. So this factor you can see from here, it was becoming 7.2 into 10 raised power, sorry, 1.8 into 10 raised power -3, this term. Okay, divided by, when we do this calculation, 1 millimeter into this term. Now this term is over here, this one, 5.4 into 10 raised power minus 4. So x becomes like this over here. But instead of doing this actual calculation, what we'll do is we will do the approximation method. So in the approximation method, we first bring this term to the numerator by putting the power minus 1. So as you can see, this is okay. So centimeters will cancel out. Now this term, let it be the way it is, that is alpha of the wood into delta T. But this second term, we are bringing it to the numerator now. Okay. This alpha of metal into delta T. And we bring it to the numerator, this becomes 1 plus 5.4 into 10 raised power minus 4 to the power minus 1. Okay. And then we use binomial approximation, that is, this power comes inside. What we're discussing about in the last lecture, that 1 plus x to the power minus 1 can be approximated as 1 minus x if x is very small compared to 1. Okay. This is called the binomial approximation method. So this is what we are applying here. This time. Okay. So this power will come inside. So next step, this will become this. Okay. Now we open this bracket. Now when we open this bracket, again the last term will be negligible because its power will become 10 raised power minus 7. Okay, so this term be something into 10 raised power minus 7. So we'll neglect this. So this is also negligible. Okay. So that is the approximation trick that we use. This term is negligible. Okay. This 1.8 into 5.4, but the power is minus 7 on 10, so we neglect that. So this becomes 4000 into this thing. Now this you can write as 1.8 minus 0.54, so that will become 1.26 into 10 raised power minus 3. Okay. And then we can do this calculation. So this is 4000 plus okay. So this is the measurement that comes. So it will be okay, these many divisions. So the measured value will be reported as, now one division is assumed to be 1 millimeter. Okay. So this is the measured value in centimeters, whereas the true value in centimeters you've seen earlier was 400.72. Okay, so this is the true length, is 400.72 centimeters, whereas the measured length is a little bit less because my scale has expanded. Okay. So therefore the error, so this is, the error will be 400.72 minus 400.62. So there's an error of, sorry, 604. So you just approximate that as 60 only. Okay. So the error is 0.12 centimeters. So the percentage error is the error divided by the value converted into a percentage. So we can say that is approximately 0.03%. Oh, just a small calculation mistake here. This should be 5.04 instead of 6.04. So just make a small correction here. we're going to have a larger percentage error. This will be the percentage error. Okay, so this is an additionally important type of application question. Okay, next thing we move on to in thermal expansion is the concept of variation of density, which will denote with the symbol rho with respect to temperature, capital T. So we know that density is mass upon volume. So rho is equal to m by v. So if at T equal to T naught, the density is rho naught, then at T equal to T naught plus delta T, the density becomes that same mass but divided by new volume. And that is 1 plus gamma delta T. So again, we use that approximation method, that this is so bring this to the numerator, and then since gamma delta T is small compared to 1, right, this is 1 minus gamma delta T. Same kind of approximation. So therefore, density varies with temperature according to this relationship. Okay. Volume varies with temperature according to this relationship. So density being inversely proportional to volume is a minus sign. Just make a note of this section first. Okay, so for example, heating a liquid from a temperature of 5 degrees C to 25 degrees C results in a 0.02% increase in its volume. So if the same liquid is heated from 25 degrees C to 65 degrees C, find its density at 65 degrees C, given that its density at 25 degrees C is 2200 kilograms per meter cube. So at 25 degrees C, the density is given to us as this much. So we have to find what will be the density at 65 degrees C. This thing we have to find out. And for that, this information is given. So just note down this section about the variation in density and now apply that concept over here. Okay, nobody's got the answer for this yet. Please try to work this out. So see, this is a bit of an indirect question. What we have to do here is, from the information given, you have to calculate the coefficient of volume expansion of the liquid. From this range, the volume is increasing by this much percentage. So T naught equal to 5 degrees C to T equal to 25 degrees C. The change in temperature is of 20 degrees C. Okay. And the percentage change in volume is this. So that means delta V by V is 0.02 into 10 raised per minus 2, or 2 into 10 raised per minus 4. So gamma delta T is 2 into 10 raised per minus 4 for delta T to be 20. Okay, so that means gamma's value is 1 into 10 raised per minus 5 per degree C. This is the information we needed. Now we will substitute the value of gamma from here into our equation for density, which we've written above. So now you can see that density is, how much is it now? 2200 kg per meter cube at a temperature T1, let's say 25 degrees C. So we want to calculate the density at T2 equal to 65 degrees C. So we'll use that relation, 1 minus gamma into delta T, where delta T is T2 minus T1. So you can see here delta T is 40 degrees C and gamma is this much. Correct? Oh, sorry. So Kunj, first of all, the density will decrease now because the temperature is increasing. Okay, so with this we complete the section on thermal expansion. Now before we discuss further, we will also talk a little bit about thermometry, or the principle of a thermometer, which is used to measure temperature. So any thermometer makes use of a physical property of a system which varies with temperature linearly. It utilizes a certain physical quantity. Suppose that is some x, which is a linear function of temperature. T. So the relationship between this physical quantity x versus temperature must be a linear relationship. For example, x could be the length of a column of mercury in case of mercury thermometer. Okay. So x is equal to L, which is L naught 1 plus alpha into T minus T naught. You can see it's a linear relationship with respect to temperature. So at a temperature of T naught, if the value of x is some x naught, then at the value of some new temperature T1, is x1. So at some unknown temperature T, the value of x becomes such that so here, if x1 at temperature T1 and x2 at temperature T2 are known values at some standard temperature, so not x naught and T naught, are known values at some standard temperature, T naught and T1, then T can be calculated for x, which is a measured value. Okay. So I'll explain this with an example. Okay, so from this formula, we can calculate the value of T from this value of x. Just make a note of this, we'll discuss. I was talking about any and every thermometer. Normal thermometer, whether it is a mercury thermometer or a digital thermometer, okay, or a constant volume gas thermometer, they all make use of this principle. This is the principle of thermometry. Okay. Now, usually the standard values for calibration used are melting point of ice and boiling point of water. Because these are two conditions which are very easy to um, create in laboratory physics. To dip the thermometer into melting ice, so achieve a temperature of 0 degrees C is very easy. And to dip the temperature, the thermometer into a boiling pail of water at 100 degrees C. So it's very easy to achieve this at a practical level. So these are the standard values that we use in this equation. Okay. Other examples are platinum resistance thermometer, okay, where X is the value of resistance R of a platinum wire. Okay. So resistance at some temperature T is resistance at temperature T naught into 1 plus some coefficient into temperature difference, where alpha is the thermal coefficient of resistance instead of linear coefficient of expansion. Okay. So for example, if R naught is equal to 1.004 ohms at 0 degrees C and at T equal to 100 degrees C is this. Okay. Then if the resistance was measured to be R equal to when the wire is in contact with a gas in a chamber. So find the temperature of the gas. Okay. So this is an example of for a platinum wire resistance thermometer. This information is given, and from this we have to now find the temperature of the gas. Just try out this question, people. Yes, very good, Kunj. That's correct. So we'll just use this formula here that okay. So this value 1.520 minus 1.004 upon T minus 0 degree C will be equal to 2.036 minus 1.004 divided by 100 minus 0. So as you can see, T minus 0 will come out to be 0.516, right, divided by 1.032. So that is half of 50, sorry, half of 100. So T comes out to be 50 degrees. So another example of a thermometer or the principle of a particular type of thermometer is constant volume gas thermometer. Okay. This works on the principle that for a gas at constant volume, let's say V naught, T V naught is equal to nRT naught or nRT. So pressure is proportional to temperature. Okay. So pressure at some T minus pressure at some T naught, okay, upon T minus T naught will be equal to this kind of relation. So again, for the standard case, if P0 is the pressure at 0 degrees C and P100 is the pressure at 100 degrees C and P is the pressure at some temperature T, then P minus P0 upon T is equal to P100 minus P0 upon 100. This equation's application becomes this. Okay, now the next thing we come to is the concept of heat capacity and specific heat capacity. So now we're moving ahead from thermal expansion concept to the concept of calorimetry. This is part of the chapter within heat and thermodynamics called calorimetry. For example, in HC Verma, you will see there's a separate chapter called calorimetry, whereas thermal expansion would have been in the chapter called heat and temperature. So, if the temperature of a solid body or a liquid or a gas, but something that is not changing state in between, if the temperature is varying with heat supplied, Q is heat supplied in joules or calories, temperatures in degrees C or Kelvin, whatever. So generally what we observe is that this is the type of graph that we get in a situation for temperature rises linearly, like a straight line, that is with heat supplied, okay, for a material, provided there is no state change. So state change would be solid to liquid. The process is called melting, or liquid to gas. The process is called boiling or vaporization. So provided there is no state change occurring during the heating, so temperature rises linearly with heat supplied for a material provided there is no state change during the process. Okay. And delta Q is equal to C delta T, where C is the heat capacity of the given material. Okay. So if we are supplying a certain amount of heat, delta Q, to achieve a certain temperature difference, delta T. The heat capacity is nothing but heat supplied per unit temperature change. So it is heat supplied per unit temperature rise. That is our heat capacity, and therefore it is measured in joules per Kelvin or calories per degree C, etc. Okay, now this heat capacity itself is a function of the mass of the material. Okay. And S is called the specific heat capacity. Okay. And this specific heat capacity is a material property. So each material has its own value of specific heat capacity. So S is equal to this kind of thing, because delta Q is C delta T, which is M into specific heat capacity into delta T. So from this relation you can see, so specific heat capacity is the heat supplied per unit temperature change or temperature rise for unit mass of the material. So it is measured in joules per kilogram Kelvin or calories per gram degree C. Okay. So for example, water has a specific heat capacity of 1 calorie per gram degree C. Okay. So find the heat needed to increase the temperature of 2.5 kg of water from 2 degrees C to 52 degrees C. So just write down the definition of specific heat capacity and from there work out this question quickly. So you can see here for this we have to just use the formula that the heat supplied is this. So you can convert this to grams because specific heat capacity is given in grams per, calories per gram. Into the temperature changes of 50 degrees C. So you'll see the unit that we'll get will be in grams multiplied by calorie per gram degree C multiplied by degree C. So that is calories. So this will be the amount of heat required. Okay. Now another conversion you should know is that 1 calorie of heat is equivalent to 4.18 joules. Okay. This is an important relation to remember. We approximate it as 4.2 joules, and this is called the mechanical equivalent of heat. That is when 1 calorie of heat is converted to mechanical energy, in the unit of energy, how much mechanical energy we'll get? We'll get approximately 4.2 joules. So that is called the mechanical equivalent of heat. Okay. So just make sure you note this down, and with this we complete today's session. So that's it for today. Wish you all the best.